the Sloan Digital Sky Survey did a wonderful study of a vast number of galaxies. It seems to be a ubiquitous quality that black holes are at the center of galaxies, and those are typically gargantuan black holes, millions or billions of times the mass of the sun. Some have suggested that early stars, which were quite large compared to more modern stars, when they exhausted their nuclear fuel and they collapsed in on each other, they created black holes that were large, and then they continued to suck in more material from the environment, and they grew larger and larger still. So that's sort of one rough way that people think about how these massive, enormous black holes may have formed, but it's uncertain. LIGO, this laser interferometer gravitational wave observatory, gravitational waves. It took headlines a few years ago when it detected the first ripples in the fabric of space. It detected them from two black holes that were 1.4 billion light years away, like 1.4 billion years ago, rotating around each other, going near the speed of light, slamming into each other, creating a tidal wave in the fabric of space that rippled outward at the speed of light. Part of it raced toward planet Earth. There wasn't anybody on planet Earth to see it at that moment, but it had 1.4 billion year journey to traverse. It raced toward planet Earth. When it's about 100,000 light years away, it grazes the Milky Way galaxy. It continues to race toward Earth. When it's 100 light years away, a guy named Albert Einstein writes down equations that suggest there could be these gravitational waves, unknown that one is already racing toward the planet, and it continues to race onward. 2 light days. It's 2 light days away when they turn on the newly refined version of the LIGO detector, and 2 days later that wave rolls by planet Earth, shakes the 2 detectors, one in Louisiana, the other in Washington State, giving us the first direct detection of ripples in the fabric of space. So these things are out there. And before the direct radio telescopic imagery from the Event Horizon Telescope of the black hole in M87, that ripple in the fabric of space was the most direct evidence that black holes are real, because when you took the way that the machine in Louisiana and Washington, it twitched for just, a tiny fraction of a second. When you figured out using supercomputers what the cause of the wave must have been, you are led to 2 black holes that are 28 and 31 times the mass of the sun. And that was the only explanation for the data. And so there's this beautiful indirect proof that these stellar-sized black holes are actually out there. And then, of course, we take a photograph of one in a nearby galaxy.
A black hole is one of the strangest and most fascinating objects in outer space. It is formed when a star with sufficient mass is dying. The gravity is so strong because matter has been squeezed into a tiny space that not even light can escape from it. A fascinating type which can reach up masses 20 times more than that of our sun are stellar black holes. However, their size is nothing compared to some of the enormous supermassive black holes with mass on the order of millions to billions of the times of the mass of the sun. Some astronomers have begun labeling black holes of at least 10 billion solar masses as ultramassive black holes. Most of these are associated with exceptionally energetic quasars. Even larger ones have been dubbed stupendously larger black holes with masses greater than 100 billion suns. However, black holes can be big or small and very counterintuitive. Some scientists think the smallest black holes are as small as just 1 atom. These black holes are very tiny but have the mass of a large mountain.
Oftentimes people think about black holes as these gargantuan structures that form from collapsed stars. There's a big one in the center of our Milky Way galaxy, weighs 4 million times that of the sun. The photograph of a black hole in the galaxy M87 that got the world excited a couple of years back, 55 million light years away, billions of times the mass of the sun. But the reality is, anything, if you compress it enough, becomes a black hole. If you take an orange and you squash an orange down sufficiently small, according to Einstein, it becomes a black hole. The flip side of it is, we also typically have an intuition that black holes are really dense, right? That's usually the way we think about them. But if you make something sufficiently large, regardless of how low its density is, it will also become a black hole. So you can make a black hole out of air. If you have enough air, sufficiently large sphere of air, it would become a black hole too, with the density of air. So all the intuitions that we typically have about black holes, that they have to be dense and they have to be gargantuan, not right.
In 1915, Albert Einstein developed his theory of general relativity. having earlier shown that gravity does influence light's motion. Only a few months later, Carl Schwarzschild found a solution to the Einstein field equations, which describes the gravitational field of a point mass and a spherical mass. Einstein himself wrongly thought black holes would not form because he held that the angular momentum of collapsing particles would stabilize their motion at some radius. This led the general relativity community to dismiss all results to the contrary for many years. However, a minority of relativists continued to contend that black holes were physical objects, and by the end of the 1960s, they had persuaded the majority of researchers in the field that there is no obstacle to the formation of an event horizon, a boundary in space-time through which matter and light can pass only inwards towards the mass of the black hole. Nothing, not even light, can escape from inside the event horizon.
And when you look at Einstein's equations, right in his mathematics, there's a little formula that you can see where it says if you have any mass m, whatever mass you want, and you squeeze it into a radius r that's less than 2 times Newton's constant 2g times m divided by c squared, speed of light squared. A formula, details don't matter. But you take any mass, if the radius within which that mass sits is less than 2gm over c squared, it is a black hole. Period, end of story, according to Einstein. But he never really believed that quantum mechanics was the true description of the world. And when he was developing the general theory of relativity, he was just thinking about gravity and not quantum mechanics. Stephen Hawking came along in 1974 and started to inject quantum mechanics into our understanding of things like black holes. And that's where Hawking proved that black holes are not completely black. He showed that black holes allow a certain amount of radiation to leak out of their surface, leak out of the event horizon, or leak out from just beyond the edge of the event horizon. And so, yes, when you think about black holes, as far as we can tell, they are a fundamental quality of the world, but you have to include quantum physics to truly understand them, and that's the cutting edge of what's happening right now.
There is a tenet of string theories and a supposed property of quantum gravity that state that the description of a volume of space can be thought of as encoded on a lower dimensional boundary to the region, such as a light-like boundary, like a gravitational horizon. This is known as the holographic principle and was inspired by black hole thermodynamics, which conjectures that the maximal entropy in any region scales with the radius squared and not cubed as might be expected. In the case of a black hole, the insight was that the informational content of all objects that have fallen into the hole might be entirely contained in surface fluctuations of the event horizon. The holographic principle resolves the black hole information paradox within the framework of string theory. However, there exist classical solutions to the Einstein equations that allow values of the entropy larger than those allowed by an area law, hence, in principle, larger than those of a black hole. These are so-called Wheeler's bags of gold. The existence of such solutions conflicts with the holographic interpretation, and their effects in quantum theory of gravity, including the holographic principle, are not fully understood yet.
There's now a connection between quantum computing and black holes. But work over the last 20 years has established that when you have a black hole, actually even more general systems, but talk about a black hole, there's an alternate description of a black hole in terms of what's known as the holographic description. It's as if there's a two-dimensional world that surrounds any given three-dimensional world that has exactly the same physics as the three-dimensional world that we're familiar with, and yet it describes it in a completely different language. So a black hole gravity is obviously essential. That's how a black hole forms. But in this dictionary that physicists have developed, there's a description of a black hole that doesn't involve gravity, only involves quantum mechanics. And the beautiful thing is the quantum processes in that quantum world mimic the kinds of processes that people have been developing for quantum computing, quantum error correction code. And there's a dictionary that people have proposed for that quantum language on the holographic boundary with physics in the interior. And the dictionary shows that the quantum error correcting code may be the reason why space-time itself holds together. So there's this bizarre way in which everything that we know about in the world around us has a translated dictionary version in a different world that lacks gravity but has quantum mechanics. And so people are using some of the insights from quantum computing to understand questions about black holes and space-time.
According to a new paper in the journal Annals of Physics, the geometry of space-time around a black hole behaves like a quantum computer, and it can encode photons with quantum messages. Ovidio Ricorian, a researcher at the General Direction of Information Technology in Bucharest, Romania, explained that the distorted geometry of space-time near rotating black holes can create and manipulate quantum information encoded in beams of light that are emitted by, or that pass close to, these black holes. In a theoretical quantum computer, a quantum computation process consists of photons traveling through a setup of mirrors, beam splitters, and prisms that switch the polarization and twisted phase of photons to values that can be mapped onto zeros and ones. The novelty of his research is the suggestion that the geometry of space-time near spinning black holes acts in an ideal manner to this setup of prisms and mirrors. This means that a spinning black hole writes a quantum code that we may decode in the near future when we come to create quantum computers. He says we are now on the verge of a new technological era, an era that will be dominated by quantum technology. We have legitimate hopes that these quantum computers will help unveil some of the now hidden mysteries of the universe. Thanks for watching. Did you like this video? Then show your support by subscribing and ringing the bell to never miss videos like this.